Hello, everybody. My name is Liz Klein. I am here from Mesoanalysis Geo program, and I'd like to welcome you to the Satellite Book Club. This is series session number 252. Today's presentation is entitled Lessons from DC Metro's Flash Flood Events. Our facilitator today is Bill Line from STAR. A few reminders before we get started. This session is being recorded. Please see the pinned message in the chat for Privacy Act information. There will be a question and answer session after the presentation, so as questions arise, please post those in the chat as well. If you are interested in presenting, there is a link in the chat to a Google form that you could fill out. And if you have any feedback, there is also a feedback form you can fill out. There are additional training assistance available through Ross Van Til. And we'd like to thank the OCLO, the GEO and LEO program offices for their support. Now let me introduce today's SBC presenter. Brian LaSorsa graduated from Penn State University in 2001 and worked at AccuWeather until October 2006. From there, Brian arrived at the National Weather Service, Baltimore, Washington, D.C. office as a meteorologist intern, then progressed to a meteorologist, a lead meteorologist, and is currently the Science and Operations Officer. His favorite weather is winter weather, and he enjoys hiking and attempting to play sports in his spare time. Now I'll hand it over to our presenter, Brian, to begin today's SBC session.
Hello, thank you very much, Liz. Can you, I guess, it looks like y'all can hear me. So good. Yeah, thank you so much. Good morning and good afternoon, depending on where you are in the country. So yeah, I'm going to be talking about the flash flood event in Washington, D.C. metropolitan area that occurred this summer. It was on July 19th of this summer. We had a localized flash flood event across that area. And I'm going to kind of be talking about what happened, of course. Then I'll go into several slides about why it happened, kind of looking at like a mesoanalysis and how did that mesoanalysis add confidence to our messaging? How did it change our messaging? Stuff like that. And then from there, I'm going to link the satellite and radar data and kind of how that supports the why. And what I mean by that is, how did the satellite and radar data support our mesoanalysis? How did it increase confidence in our messaging for this event as it drew closer? Then we'll take a look at what some of the convective allowing models are showing about 12 to 24 hours out in advance. And then from there, we'll just take a look at some takeaways and some guidance that I recommended for our staff as far as deciding when to issue the flood watch for flash flooding, 12 hours out, 24 hours out, what parameters are we looking for, and, what can maybe help us make those decisions going forward for these types of events that are localized but very highly impactful. So you can go ahead to the next slide. Testing. Next slide. Yeah, and so you can see here, looking at the rainfall amounts there, we had about 2 to 4 inches across the DC metropolitan area just north of the District of Columbia. Now, most of this rain fell within an hour period. So we actually had instantaneous rainfall rates on our radar, looking at about 4 to 6 inches at instantaneous rainfall rates. So this was very heavy rain in a very short period of time. And you can see here in this zoomed in image here that we had about 2 to 4 inches of rain in the northern suburbs of DC, in the northern parts of the District of Columbia. You can see Silver Spring in that area tended to be the hardest hit. Go ahead to the next slide. You can see on the next slide here, this is basically some of the reports that we had. Giving that amount of rainfall in that short period of time in that area where it's very urbanized, we have excess runoff that occurs. And you can see here we had a bunch of flash flood warnings out. At one point, we actually upgraded to a flash flood emergency in collaboration with the Montgomery County EM. The Montgomery County EM also reported rises of 10 feet within 30 minutes along the Sligo Creek gauge. So if those of you who are unfamiliar, the Sligo Creek goes through, an area that there's a floodplain there, but there's a lot of walkways and bikeways, bike paths and walkways in those areas. So having that 10-foot rise in 30 minutes is obviously very, very, very dangerous and an immediate threat to life and property. And you can see we also had numerous water rescues as well in that area. The emergency manager for Montgomery County, actually, when I talked to him on the phone during the event, he mentioned that it was the worst he's seen there since 2011. So that's been about 14 years. So even though it was a localized event, it was highly impactful with moderate to major flooding across that area. Go ahead to the next slide. Be a bit of a computer issue because I don't see the next slide yet. Okay, so sorry. Yeah, so it says, why did that happen? So let's go into the Mesoanalysis a little bit. So go ahead to the next slide there. You can see on the radar imagery here, it should be a loop. I'm not sure if it's looping, but if it isn't, go back to that slide. Yeah, so here, yeah, that's the radar imagery there. You can see it was a loop from 19Z to 1945Z. What you'll see basically is that there are two, what I call remnant MCSs. There's one across the eastern panhandle of West Virginia there that's moving west to east. And then there's another one across central Virginia that's moving west to east as well. As those systems approached, they added a little bit of mid-level moisture to the area, and we'll look at that in some future slides, but also across the DC area there, you see some lighter reflectivities, and perhaps later in the image or the loop there, you'll see some linear features there. There was actually a little bit of a boundary that was setting up that was kind of east-west oriented across the northern parts of DC and the District of Columbia itself as well. So go ahead to the next slide for the satellite. You can see here on this satellite imagery, you can see the thicker and more dense cloud cover. This is the geocolor around 1921Z. And again, the event happened around 21Z. So this is about an hour and a half to 2 hours roughly before the event occurred. You can see some thicker, more dense cloud cover to the north. And again, a similar situation to the south as well. But in between those two systems there's actually a little bit of heating going on. And you can see at the top of the red hour there, you see a Q field kind of building and developing where we saw that boundary on radar over the northern parts of the district and then the suburbs across Silver Spring and in that general area there. So that kind of grabbed the attention immediately from forecasters, seeing that differential heated boundary setting up across that area. And then we'll go to the next slide as well. Let's go for the next slide, and I'll show you a couple of things about the steering flow and whatnot. So again, we noticed on the previous slide, we did notice that the orientation of that differential heating boundary was west to east. And here you can see a couple radar imagery here. I took a still imagery just to show you where the boundaries seem to be setting up. This is the terminal Doppler radar out of BCA. And you can see on the bottom right there in the velocity. Now, the terminal Doppler radar is located to the south. It's towards the bottom of the image there. So the red is essentially velocities moving away from the radar. And then towards the north, you see green, which is moving toward the radar. So it's very faint, which is showing weak magnitude of wind. But there is indeed certainly a southerly flow converging into maybe a little bit of a light northerly flow, or certainly at least some speed convergence there. And if you look at the top left, that's the reflectivity imagery there. And you can kind of see some light returns across those areas. I tried to circle them a little bit just to give you an idea. So you can kind of see that the general orientation of the boundary is west to east. And you saw on the previous slide that the orientation of that differential heating boundary is west to east as well. So if you go to the next slide, you'll see the boundary maybe tightening up a little bit on the next slide. Yep. So go one more slide. So yeah, so here you can see that the boundary did indeed strengthen. You can see some darker red colors, and you see a little bit of on the bottom right imagery there at 2029 UTC. And again, this is about a half hour before the event really got going. You can see some green, which is moving towards the radar, and red moving away from the radar. So stronger convergence across the District of Columbia and southern Montgomery County in that area. And then you go into the top left, and you can actually see some cells starting to develop as well across that area. So at this point, we're kind of eliminating the conditional probabilities that our storm's going to develop because they are. So now we're kind of shifting that unconditional probability where we have a highly impactful event that's certainly those chances are increasing that that's going to occur across this area. So go ahead to the next slide. So I just wanted to show you, we looked for ACAR soundings. Unfortunately, they didn't have ACARs, but they did have the initialized HER data, so your HRR. You can see here in the sounding. So this is at Dulles Airport, which is about 20 miles to the west or so, but it's pretty close. And just wanted to show a couple features here. If you look at the sounding there, between about 600 and 700 millibars, you see a little bit of a subsidence inversion. And then you also look at the winds up and down throughout the atmosphere. It's generally west southwest to east northeast, and you can see that in the hodograph as well. So pretty close to a west to east orientation there. So your cloud layer winds are parallel to your low level winds. So if you do get cells that are developing, you're going to have training convection repeating over the same area, given the fact that the winds are unidirectional with height. And like I mentioned, you do have that substance inversion. So, it's kind of, we're a little bit unsure whether convection is going to develop or not, because you have to erode that inversion. And if you go to the next slide, a couple things happen here, and I kind of pointed the arrows. You see the moisture increase there in the mid levels there. And with that moisture increase there around 700 to 600 millibars, the temperature actually decreased. So that we eroded that mid-level substance inversion. And I theorize that that's because of the remnant MCSs that we're coming across. That moisture advection also came along with some cooler temperatures in the mid-levels as well. And that allowed thunderstorms to grow and continue to develop and train over the same areas. And then also, if you look at the low level wind, we noticed it was generally west to east or west southwest to east northeast. Looking at the low level wind here, it actually back to the south. So that tells me that the boundary actually came through that area as well, which also helped enhance the convection as well. So in this image here, we actually have more instability, and your precipitable waters are over 2 inches. So you're in a really favorable environment. And so if you go to the next slide, I've kind of tied it up with the mesoanalysis. Okay, so looking at here, I have just put a couple images here, and I'll explain what they are. And again, this kind of goes hand in hand with what we were looking at in the previous slides. So this is about an hour before the event. On the left-hand side, this is the 20Z. It's called precipitation potential placement. And essentially, that's the average of the 1,000 to 700 millibar humidity combined with the precipitable water. Studies show from Storm Prediction Center that as you get values over 1.6, those tanner, orange colors you see in the image there, that's indicative of a lot of moisture in the atmosphere. And then you see those red lines as well. That's a 0 to 2 meter convergence. So you can kind of see over the DC area, not only do we have very high values of precipitation potential placement, but it's also co-located with some stronger low-level convergence as well. So that is indicative of storms developing and flash flood threat increasing across that area. Going to the middle imagery, that's the precipitable water across the area. Where you see those hatched areas around the District of Columbia, that's essentially precipitable waters of about 2 to 2.5. So very juicy atmosphere indeed. So any storms that do develop can produce very heavy rainfall. And then you shift over to the right one more, and you got about 3,000 to 3,500 joules per kilogram of CAPE co-located with the high instability and co-located with the low-level convergence. So when you factor all these factors together, you can see why we had an anomalous event. Even though it was localized across that area, you had a lot of instability that caused deep cores to develop. You have a lot of moisture in the atmosphere that sort of producing very heavy rainfall, and you have a low level a source of low level lift to combine with that instability to produce that very heavy rainfall and those thunderstorms. And you have a training element because you have a boundary that's oriented west to east, and that lines up with the steering flow as well. So when we kind of saw all this coming together, we did actually issue a watch about an hour or two ahead of the event, because we saw on our mesoanalysis that indeed this event was taking place. So instead of having the low confidence because you were unsure if convection was going to develop, but if convection does develop, it's going to be highly impactful, we kind of eliminated that low confidence because we eliminated the condition, because storms are indeed going to develop. And we kind of saw that off the mesoanalysis and off the satellite imagery. So go ahead to the next slide. And so we're going to talk about how the satellite and radar is data supported why. So what I'm getting at here is we did our mesoanalysis, and I kind of want to show you how the satellite data added confidence to our mesoanalysis. It was basically a confidence booster, it was a confidence nudger. And so, yeah, the more confidence you can add as a forecaster, the better, the more confident you're going to be in your message, the more confident you're going to be in your forecast, and the better products and services you can provide. So I just kind of want to show you how satellite supported our operations during that time. So go ahead to the next slide. I think it's still loading. Not sure. Bear with me. Does anybody see the next slide?
Yeah, we see it. It's your satellite one with the radar inset.
Okay. Yeah, apologies. Let me pull up the presentation real quick because I don't see it on mine.
Slide 17.
Thank you. Hey, I'll pull it up here. Yeah, so if you are seeing it, hopefully you're seeing a loop of the geocolor imagery there. And you can kind of see those two features. Now, this is before through after the event, so 17 through 22Z. You can see that if you look at the imagery to the top left there, you can kind of see one feature moving to north. I kind of showed you in a satellite slide earlier. But you can also see the differential heating boundary set up there, the Q field built up in that area, and then you see the flare up of convection. And again, if you look at the motion of all the clouds, everything's west to east roughly, particularly at the mid and upper levels, and that adds confidence to what the wind flow is. So when we see the orientation of that boundary matching with what the satellite data is showing us, that is showing that we indeed have training convection, and not only training convection, but also deep, strong convection with heavy rainfall, because you see that flare up in the Q field and the cumulonimbus clouds building in that area, and that orientation parallel to steering flow. The image I just attached to the bottom right there is just to show you that, that boundary again is oriented more west to east. I just wanted to give you a little example of that. So go ahead to the next slide. Yeah, so this slide here is showing basically it's a combination of visible satellite and the infrared satellite, and I thought it was kind of cool because not only again is it reinforcing what I just mentioned previously, you can see the west to east movement, you can see some of the cooler cloud tops coming in there with that dense overcast with that southern system to the south of DC, the differential heating boundary, but then at the very end you can see the flare up of convection that was indicative of the strong storms that developed in the DC metro area there towards the end of the loop there. And you can see the overshooting cloud tops for a little bit as well. And again, you can see that training element indeed. Even in the Q field, you can see like a west-southwest to east-northeast movement as well. So you can generally have that unidirectional flow that you can see in this satellite. And if you look down to the south, I thought it was kind of interesting too, as you get down towards central Virginia, if you're not familiar, it's basically that's really deep, cold clouds that you see in the middle of the image there across like Charlottesville, Central Virginia, in that area. That indeed produced very heavy rainfall as well, but that was actually moving more, that orientation is more southwest and northeast, so it wasn't quite as parallel to the steering flow. So we had more of a training element to the convection across the north than we did across the south. Now, still produced very heavy rainfall, but that training element to the north is what made it from a flash flood situation to a more highly impactful flash flood situation where we had moderate to major flash flooding in that area. So go ahead to the next slide. You can see here in the water vapor imagery, it's a similar situation. You can kind of see the moisture advection coming in from the west. And again, if you remember that sounding I showed you, you had that cooler air at the mid levels, that Dulles Acres HER sounding. You can kind of see why here we were indeed getting moisture advection, and you can see that on the water vapor imagery, and that moisture advection helped cool the mid levels as well. And of course, you can see the flare up of convection as well towards the end of the loop over the DC metro area. So again, just kind of reinforces what we were talking about earlier when we did our mesoanalysis. Go ahead to the next slide. Not sure if you can see it. Yeah, so this is the precipitable water here. This is the blended TPW on the top. And then, of course, I put the mesoanalysis. Now, this is at 21Z. That's pretty much when the event was occurring over the area. And this is just to show you, again, just kind of reinforces our thinking that we are in indeed a very juicy atmosphere. That red you see across the mid-Atlantic is precipitable waters over 2 inches. And that matches the mesoanalysis over the DC metropolitan area as well. So I just wanted to show that in addition to the other satellite data we're looking at as well. Go ahead to the next slide. So here you're just basically looking at a radar loop of the event, at least the initiation of the event. Again, you can see that flare up of convection. And note, you see the boundary that's oriented west to east, roughly around the District of Columbia, and you see the orientation of the convection parallel to that boundary. And again, you couple in the fact that you had the steering flow, that's why you had the training convection in that area. And again, we certainly did have heavy rain and even some flash flood warnings to the south and west across central Virginia. But you see that convection overall is a little bit more progressive. And again, that's because it was oriented differently. This is why mesoanalysis is very important. And this is why mesoanalysis can help with messaging during and leading up to events. Go ahead to the next slide. And this here is basically looping the end of the event, so to speak. You can see everything at this point kind of becomes outflow dominant. If you look to the south, you can see that boundary drifting from north to south. And then if you look to the north, you see another boundary going from south to north. So basically, we had a lot of convection. The cold pool developed. And it took a while, but eventually the cold pool allowed the atmosphere to be more stable. We used that energy that was in the atmosphere, and the convection started to disperse away from the southern Montgomery County, Silver Spring, northern DC area. What's interesting to note here is I noticed that there was a lot more convection on the northern side of the outflow boundary as opposed to the southern outflow boundary. So you see the one going to the north, it seems to be firing up more convection in Montgomery and the Howard counties and got very close to Ellicott City. But then you look to the south, you don't see as much. Not 100% sure. My theory is that we had a much thicker overcast from the southern MCS feature. And I think it was a little bit more stable in that area to the south as opposed to the north, where we had more breaks of sunshine and that MCS was a little bit weaker. So that's my theory as to kind of why the convection survived going to the north, but didn't necessarily survive going to the south. So go ahead to the next slide. So we're going to take a look briefly here at what the convective allowing models are showing. Go ahead to the next slide. This is the HREF 3-hour probability match mean from 21 to 0Z. So essentially late that afternoon and the evening. The image on the left is the run from 0Z the night before. The image on the right is a run from 12Z. And I just kind of wanted to show, if you look at the overall probabilities, now the tan lines are essentially probabilities greater than an inch. So if you're looking at the image on the right, per se, you're looking at a neighborhood probability of over 50% that you'll get an inch in that 3-hour period. But and then the red lines are probabilities of greater than 3 inches. So there's actually an elevated, although lesser, but still elevated probability that you'll get 3 inches in that 3-hour period. And just knowing that the environment that you're in, that if you do indeed get convection developed, it's going to be produced very heavy rainfall. So you can probably assume that most of this is going to be falling within an hour or so. So there were some hints in the HREF, certainly looking at the neighborhood probabilities that we were going to get some heavier rain to the north, but the confidence was higher to our south, where we had that more larger scale system that was moving through. So go ahead to the next slide. And I'm not sure if you can see it yet, but on the next slide, you're looking at the 0 to 3Z on the HREF. Again, similar features there. You can see the elevated probabilities of over an inch and even over 3 inches. And there was a little bit of a trend upward between 0Z and 12Z, just looking at the overall probabilities for that to occur, the neighborhood probabilities, that is. Certainly, if you look at the bullseyes there and the average QPF, it was very localized, but nonetheless, you can see a trend upward in at least the overall probability of some heavier rain getting into the DC metro area in that guidance there. Go ahead to the next slide. So this here, we'll gradually loop through this a little bit, but basically on the left, you're looking at the HRR, the HREF model for 15-minute accumulated precipitation. And I'm not sure if it's looping or not, but what you would see is that the precipitation, those red values you see are essentially over an inch in 15 minutes. That's very heavy rainfall. I mean, if you multiply that by 4, that's over 4 inches in an hour. So that's very heavy rainfall amounts. And you can kind of see the stuff to the north around the DC area, even though it's more localized, it's kind of slower moving. And I think it's picking up on that training convective element. And then the stuff to the south and west over central Virginia is a little bit more progressive. And that's picking up on the fact that just the orientation of that convection was a little bit different. And then on the right-hand side here, you can see this is basically the overall total precipitation. And, the 12Z HREF actually did show, over 3 inches, pretty close to DC, although being very localized, nonetheless, it did show it there. So when you couple that with what we were seeing in convective, or in the neighborhood probabilities, there was certainly some hint that there's going to be some heavy rain across that area, although it was going to be more isolated in coverage. So if you want to go ahead to the next slide, and you may have to page through the loop a little bit. This is basically the overall takeaways. So again, we had moderate to major flash flooding occurring over the DC metro area, and again, the reason was it was challenging. Anytime you have an isolated event with you have lower confidence for the event to occur, but potentially high impact. That messaging can be very difficult. I've always struggled with that. I think I'll struggle with that to the end of my career. So I'm always open to different interpretations on how to handle these types of events. But the Mesoanalysis was very important, and at least we were able to catch up before the event actually occurred, and getting a watch out and messaging that to our partners, and then issuing the appropriate warnings from a neighborhood perspective, from a radar perspective. Again, the thermodynamic profile pattern was very favorable, and again, they were showing, particularly with the neighborhood probabilities. So some of the advice I gave to our staff here for these situations is when you certainly have the potential for very high impact, and that's what we're talking about is high PWATs, high instability. Well, that if this heavy rain occurs over the wrong area, we're going to have a significant flash flood issue. To be maybe a little bit more progressive with that, and use neighborhood probabilities as opposed to average ensemble or any one particular model. And I think that can help get the message out that even though we have low confidence, this could be very highly impactful. So that's kind of what we're looking to do in the future. You start seeing elevated probabilities for 3 inches. That should hopefully be getting our attention a little bit. And then if the pattern is unfavorable from a temporal standpoint, maybe you treat it more like a severe watch. And what I mean by that is maybe you wait till an hour or 2 or 3 or whatever before the event occurs, because you don't anticipate a highly impactful situation, and you also don't see some of the signals for flash flooding across that area. So that is all I have, and I will pass it back to you all for any questions or comments. I apologize for any technical issues.
All right, Brian, thanks for that excellent presentation. No, I think it worked out. It worked out great for us. We were able to see everything and hear you fine. And thanks for presenting on a relatively recent topic. It was nice to hear about an event that I'm sure is relatively fresh in the minds of many folks who are on this call. So next we're going to turn to the Q&A. Now is the time to get your questions into the chat. Please get them in there and we'll answer them in just a minute. But first, I think you all know the drill. We have our friendly reminders. First, to view the facilitator and presenters during the Q&A, I guess if you want to view our faces bigger, please change your layout from tiled to hide tiles without video. I also want to mention that in 1 week, we'll have another excellent presenter. So that'll be on Thursday, September 25th at noon Eastern, same time, same place. Jeremy Michael from the Weather Service will be talking about Gremlin in Appalachia from the testbed to use in operations. Recall from previous SBCs that Gremlin stands for the GOES radar estimation via machine learning to inform NWP. We've heard about that algorithm in the past, and it'll be really great to hear how it's actually being used in operations now. And finally, if you have additional questions about the Satellite Book Club or just satellite products in general, please contact Sheila Coupe from the Tower S team. So now to the questions. Again, please put them in the chat. If you don't have questions, I have many to pepper Brian with today. So first, Brian, I wanted to ask for this type of event, are you and is your office leveraging or requesting mesosector imagery? And how is that useful? How is it useful to have 1 minute imagery during this type of event? Can you unmute yourself?
Yes, can you hear me?
Yep, go ahead.
Sorry about that. Yeah, certainly we've done that in the past. And certainly having that more temporal resolution to the data, you can see storm scale evolution, you can see, boundaries setting up, so I will say most forecasters would probably use the SBC Mesoanalysis the most leading up to an event, but certainly having that type of satellite data can only help. I think when you're talking near term and you're getting within a few hours of events, you kind of maybe shifting away from model data at that point and be more reliant on observational data. So certainly that can be a big help, of course.
Okay, very good. Jarrell from Sierra asks, when you view satellite information in operations, are you accessing the data primarily in AWEBs, or are you also viewing satellite data via some online web pages?
So yeah, I would say both. It depends what forecaster. So a lot of forecasters do use the online sites. I know I use that as well, and it also helps because on our intranet page, I've actually downloaded all the quick guide references to the different types of satellite data there are. So it hopefully helps myself and our other forecasters as well really understand this, what the purpose of the different types of satellite data is and how it can be used in operations. So we certainly use it online, but we also have access to a lot of that in AWIPs as well. So I would say both to that question.
Very good. Reminder, please get your questions to the chat. There are no dumb questions, or so I've been told. You talked about how the satellite imagery was useful for kind of assessing motions of the clouds and basically, motions in general. Do you ever view satellite-derived winds, such as what's in AWIPS or online, those derived motion winds? You cut out again, Brian.
Oh, sorry. Yeah, we've done that certainly as well. And I look at them as confidence nudgers, right? Like, you may look at the Mesoanalysis and then look at the some of the cams and say, okay, this is what I think is going to happen. This is why I think it's going to happen. But I look at it as just building pieces of confidence. So like certainly the more data you have that supports what you're thinking is going to add more confidence to your forecasts. And I think that'll also help with your messaging as well. So yeah, we have done that before, and hope to continue to use all that valuable satellite information into Tower S, and you all have provided for us. We're very thankful for that in operations, of course.
Awesome. All right, another Brian from the Weather Service has a question. Brian, you mentioned that the HREF and HREF showed signs of heavy rain potential, but it wasn't necessarily right over the area that ended up getting the flooding. So are heavy rain signals in the area good enough for your office to message higher impact heavy rain, or do you feel like we need to do more to get the location of that heavy rain correct?
So let's make sure you can hear me first. Okay, cool. Yeah, so certainly in a perfect world, we would get the location correct all the time and there would be no uncertainty. But obviously, we don't live in a perfect world. And when you're dealing with this type of localized convection, oftentimes, at least anecdotally, I've seen that we can determine that it's going to happen and in the general area that it's going to happen, but we never know exactly where. So when you do have localized convection and you have an environment that's supporting very heavy rainfall based on what we did in the Mesoanalysis leading up to that event, that to me is you enhance that messaging by using neighborhood probabilities, because not necessarily 100% sure of exactly where that convection is going to develop. And that's why I kind of hit up saying, hey, when you're in a really bad situation as far as all of the atmospheric conditions and parameters are lining up for very heavy rainfall, and it's somewhere near your metro areas where we obviously know they're urbanized, and the impervious urbanized nature of the metro areas, combined with the fact that that any heavy rain would cause significant flash flooding alone, that to me leads me to lean more towards the neighborhood probabilities. Perhaps I would lean less towards the neighborhood probabilities if I thought that maybe the heavy rain was going to be in an area that wasn't flash flood prone, or maybe the heavy rain was we didn't think there was going to be very heavy rainfall based on our analysis from a mesoanalysis. So to answer your question, Brian, I don't know if I did and all that, but to answer your question, I think the exact area, it would be great to have, but we're kind of looking for general areas, I think, because it's very difficult, especially with lead time, to pinpoint exactly where the heavy rain is going to be. So I kind of focus on neighborhood probabilities in these events.
Great. Thanks, Brian. We still have time for more questions, folks, so please get them in the chat. I'm curious, Brian, about lightning data for this type of event. What role maybe does lightning play in your office, specifically maybe GLM, in these convective or heavy rain events?
Yeah, certainly a very big role, because obviously testing. So certainly a very big role, because obviously lightning is, when you get lightning jumps, we call it, there's a co-located with stronger updrafts. So in a flash flood setup like this, lightning data is very important, because if you're obviously getting a ton of lightning over the same area, you have very heavy rainfall associated with that as well. And then also from a severe standpoint, lightning jumps are co-located with stronger updrafts, which lead to severe weather. So if I'm sitting in a really high decape event, right, that's pulse convection or multi-cell convection, and I see a ton of lightning develop, I know I have a strong core. That is a storm I indeed want to interrogate for potential severe thunderstorm warning for damaging wind. So yeah, lightning is very helpful. And then of course, the GLM is very helpful, obviously, for IDSS as well, right? If there's outdoor events and whatnot. And we use lightning cast as well a lot. That's a big help in the summertime. Yeah, they're doing a fair in whatever county, is lightning nearby. We do use lightning cast to help with our IDSS messaging as well.
Nice. Yeah, nice to hear that. You're taking advantage of some of the new tools available. So kind of on that note, can you acknowledge any maybe knowledge gaps as it relates to use of satellite information in your office? Maybe areas where training could be bolstered or improved, availability for you guys?
Yeah, certainly. I would say, and this is myself included, not just the staff. Yeah. There's a lot of information out there, a ton of information out there, and I think there's certain levels to understanding something. From an operational standpoint, as long as we know what the strengths and limitations are of this product or whatever product it is, and how it can be used in operations, something simplified like that. That's why I kind of referenced the quick reference guides that I put on the intranet. So I'm trying to simplify that to make it very applicable for our operational meteorologists. And then there's being an expert in it and understanding what's underneath the hood and whatnot, which we have a couple forecasters to do that as well. So I think just simply with all the information that's out there, is putting something that's very easy, concise for operational meteorologists to use and be able to select from, when they're doing a mesoanalysis in this case, and not just this, but like winter weather, on the synoptic scale as well, stuff like that. So just something that's clear, concise, and short and sweet, so the operational meteorologists understand how to use that and where to get that information from.
Yep. No, that's excellent. It's not just satellite. There's a bunch of information forecasters leverage, and yeah, for us to be able to get you that quick hitting guidance is, I agree, very important. Any more questions? Last chance to get them in, and I'll ask one maybe slightly more general question, kind of a wish list question. Can you think of any certain observational fields or variables that you feel are missing from your suite of observational tools that might be helpful during this event or maybe any convective event?
Testing. Sorry, sometimes it takes my mic a minute to jump in. I know I was talking to Lee Burrell from the Tower S, and they were talking about having more microwave imagery where we can get like sounding profiles anywhere. That type of data would be very valuable for just a multitude of reasons. On the severe weather, or from the severe weather standpoint, you can do more analysis on the mid-level capping inversion. Is it stronger than what the guidance has? Is it weaker? So you can do model diagnostics off that, and you can do the same thing in winter as well. So it's more data in the vertical that's easy to see, and the updates frequently with time would be on my wish list, I guess, if I could flip a switch.
Well, on that note, do you guys use new caps in your office?
Yes. Yeah, you certainly use new caps. So we do have some data in the vertical, but it would be cool to get like a sounding at any time, but just simply clicking like on a location area, which again, we do have that in new caps to a certain degree. But there are some limitations with it, but in a perfect world, it would be just easy to have maybe a tool enabled, so you just simply pull it up and just click anywhere and it pulls the sounding right away. I don't know.
Yeah.
Again,
or maybe like a sounding from geo orbit with the higher temporal resolution, still obviously coarser than a radiosonde, but yeah. Right.
Yep.
Yes, exactly, Liz. Like maybe something like a GXS. Like I figured, folks on the call, including Sheldon, very close to the center of this event, receiving lots of rain. All right, if there are no more questions, I think I've exhausted my list of questions. Brian, you've been excellent. I learned a lot. I look forward to chatting to you in the future about all things satellite and operations, and I will hand it back to Liz.
Yes, Brian, thank you for your recent and relevant presentation today, and thank you, Bill, for your wonderful facilitation. A reminder that 1 week from today, same time, same place, we'll be hearing from Jeremy Michael on Gremlin and Appalachia, from the testbed to use in operations. Thank you, everybody, for being here today. Take care.